Before we get into the portion of the course dealing with integration, which is going to almost exclusively take up the rest of the semester, there's going to be some other stuff thrown in there. We'll talk about series and what are called Laurent series and power series. We'll talk about different theorems involving integration, but integration is going to take up a lot of our time that we have remaining in this course. But before we do that, specifically because this is an online course and because I feel like what we've done so far, I've kind of picked and choose some topics, and I want to just take a break from doing anything new, and I want to do just a quick recap of all the stuff that we've talked about so far. Okay, and so this is, I'm not going to say anything new in this video. This video is just to kind of take a step back and realize that we've actually done quite a lot so far. Probably it feels like we've done quite a lot so far to you, but I just want to put everything kind of in a context and talk about the things that we've talked about so far. So we started this course by describing complex numbers, and you can do it formally by thinking of as pairs, say x comma y, or you can write it in the usual as a usual complex number x plus iy, where the real part of z is x and the imaginary part of z is y. When we talk about complex numbers, we're specifically talking about numbers of this form, so x plus iy. That includes the real numbers and the imaginary numbers. So when we talk about imaginary numbers, an imaginary number is just where you have this iy part. Okay, so whenever you hear someone say an imaginary number, they don't really mean a complex number. They mean just an imaginary part. And then we'll say that it's a complex number if it has a real and an imaginary part. Okay, so anyway, so this is a complex number. We've talked about the complex conjugate, which is x minus iy. We've talked about the modulus of z. Okay, so that's the, basically if you think of complex numbers, you can think of them on a plane, and then the modulus of a complex number is the distance on the plane to the origin, or it's also given by the square root of the real part squared plus the imaginary part squared. And with the modulus was the argument of z. And then of course, this started the whole discussion of the branch cuts and in choosing which part of the branch, because if we talk about the argument, all we're talking about is that if you go some angle theta, then you could also go 2 pi plus theta, right? You could go around again. And then any value that's going to be theta plus an integer multiple of 2 pi, you can think of as the argument. So we have to kind of decide once and for all, what are the angles that we're going to use? And as we talked about in actually just the previous video, or one of the previous videos, is we're going to talk about the principal branch being from negative pi to pi. Okay, so that turns out to be the most commonly used branch, but you can actually do lots of complex analysis over other branches. It's just that picking one and going with it is the nicest, most systematic way to deal with this. So anyway, so that's the argument of a function. We talked about the roots of unity. So the roots of unity are the solutions to the equation z to the n equals 1. And once we talked about the polar form of a number, so z being r e to the I theta, then finding the roots of unity turned out to be pretty straightforward. Okay, so finding the roots of unity, we had a formula specifically involving polar form. Okay, so I'll let you go back and look at that. One other thing that's true with equations like z to the n equals 1, this is a polynomial of degree n. And it turns out that there's what's called the fundamental theorem of algebra. I'm not sure if I explicitly mentioned this or not. This is a really deep theorem that's going to be beyond the level of what we can prove for now, but at least we can state it. And that's that every polynomial of degree n, so every polynomial of degree n, I can't spell, that looks terrible. So every polynomial of degree n has n solutions. Okay, so it has n roots, I should say, up to multiplicity. So z to the n equals 1 has n roots. And really put any, take any polynomial that you want, as long as it's of degree n, you'll have n roots. This is different than what happens in the real case, right? If you were to have x squared plus 1, there's no roots, because x squared equals -1 has no solutions, but over the complex numbers it does. And it turns out that once you allow that, then you actually get roots of every polynomial. Okay, so that's the fundamental theorem of algebra. What else do we talk about? At this point, we also talked a little bit about topology. So we started by talking about paths and parameterizations of different paths. So remember that we're cheating just slightly. Usually we think of a path. So we have some curve, right? So whatever the curve looks like, I don't care. But we have some curve gamma, and gamma specifically refers to this curve, this line segment, this geometric object. But we also use gamma to denote the function that we use to represent the curve. So gamma of t, typically from some range from a to b, that's going to be our path. And so this is, we're slightly cheating, right? So for example, if you were to have a circle, then you have gamma would be a circle, but your gamma of t would be e to the it or r e to the it, depending on the radius. And so we're kind of confusing both the geometric object and the function that describes the geometric object, but it turns out that that's generally okay. Okay, so there's a little potential for confusion there, but that's that. And one other thing just to keep in mind, paths have directions. And so if we change the direction, then we get a different path. Okay, and so we'll talk about that, and that'll have some consequences for us when we get to integration. So that's paths. We also talked a little bit about topology, like what it means to be an open set, a bounded set, what it means to talk about the boundary of a set, the interior, what it means to be an accumulation point, an isolated point, an interior point, and so on. So there's all sorts of stuff that we talked about in the topology section. We talked about limits. Okay, so we talked about limits, and we gave an epsilon delta definition of a limit for complex variables. This was very similar to the limit definition that you get in a Calc 3 course where you have a multivariable function. It's basically the same, actually. With limits, we talked about differentiability. Okay, so what it means to be differentiable. And one step beyond that, what it means to be holomorphic. So remember that a function is going to be called holomorphic at a point if the function's differentiable at that point and differentiable in some small neighborhood containing that point. So as long as it's differentiable in a small, say, circle or disk containing that point, then it's holomorphic at that point. So holomorphic means it's differentiable plus it's differentiable nearby. That's the way to think about differentiability. That's different than just differentiable. So there's points that are differentiable, but they're not differentiable anywhere near it. So in particular, they're not holomorphic. Okay, and then with that, if a function's differentiable everywhere and therefore holomorphic everywhere, then we said that the function's entire. Okay, and so entire functions are ones that are differentiable everywhere. So that's like z squared or e to the z, or all the usual nice functions that you work with are generally going to be entire functions. If you have a rational function, that's not going to be entire because it's not going to be continuous nor differentiable in the denominator, but that is what it is. So, so most of the nice functions are going to be holomorphic on their domain, and if the domain's all the complex numbers, then it'll be entire. We also saw that any function that's differentiable at a point has to be continuous at that point. So differentiability implies continuity. So if a function's differentiable at a point, then it's also going to be continuous at that same point, and we proved that. Next, we talked about conformal functions, so what it means for a function to be conformal. And there's a nice geometric description, and that's that if you have two paths that intersect at a point and the point's holomorphic, if the function's holomorphic at that point, then the projections, the images, I should say, of those two paths are going to be somewhere else, maybe. They'll intersect at f of a. If they intersected at a, then the images of the paths are going to intersect at f of a, and importantly, they're going to intersect at the same angle. So we can think of conformal maps as kind of angle preserving maps. So they're maps that preserve angles of paths. So that's conformal functions or conformal maps. Next, we talked about the Cauchy-Riemann equations. So Cauchy-Riemann equations tell you that if you have a differentiable function, then there's a nice relationship between the partial derivatives of the function. So the partial derivative of f with respect to x and the partial of f with respect to y, there's a nice relationship between those if the function's differentiable at a point. And then in particular with Cauchy-Riemann, but actually before we got to Cauchy-Riemann, we talked about what it means to talk about those partial derivatives. We talked a little bit in chapter 3 about Mobius transformations. Okay, so Mobius transformations, these are particular type of fractional linear transformations. So Mobius transformations. And then we most recently talked about limits at infinity. So limits at infinity, this includes, there were 3 types of limits at infinity. This is when the limit is equal to infinity, the limit as z goes to infinity, and then possibly both, right? If you have the limit as z goes to infinity and that limit's equal to infinity, then we had to just kind of carefully go through the definitions in all cases there. And then after we talked about infinity, we talked about the extended complex plane. And with that came stereographic projection. So the extended complex plane, but also stereographic projection. So stereographic projection. And the extended complex plane via stereographic projection can be put into one-to-one correspondence with a sphere. That sphere endowed with the usual stereographic projection is called the Riemann sphere. So in that context, that's called the Riemann sphere. It's just a sphere of radius 1 centered at the origin where the equator goes through the complex plane. But all the nice topological properties of the Riemann sphere are why that has his name. So that's why it's named after, this is the same Riemann that we see all over calculus. Okay, so we talked about the Riemann sphere. We also talked about, and I kind of skipped over this, Euler's identity, so e to the I theta. This turned out to be a really nice key into how we talk about polar coordinates for different numbers. And so this e to the I theta is cosine theta plus I sine theta. And again, this is very useful when we're talking about polar coordinates. We also talked about the principal branch of the logarithm. So this is the natural log of z plus I arg z. And this arg, here we use capital L and capital A to denote that we're talking about the principal branch. So the principal branch is, so arg z is going to be somewhere between negative pi and pi, including the right endpoint, not including the left endpoint. And we talked about all the properties that the logarithm has there. Okay. This I think is this is not an inclusive list at all, but I think this gives us an idea of all the stuff that we've talked about. I guess I also did a few videos over particular functions, like f of z equals z squared. We talked about what that function looks like when you were to graph it. Now, when I say looks like, what we did is we took the complex plane and colored it, and then figured out if we apply this function to each point in this plane, what does the image look like, right? So we're talking about two-dimensional maps to two-dimensional maps, which are in a certain sense four-dimensional objects. So you have to color them to kind of keep track of where all the points go. But we talked about these functions like f of z equals z squared, f of z equals square root of z. So if z is r e to the I theta, then the square root of z we define to be the principal square root to be so this is the principal square root of r times e to the I theta over 2. And there's some good geometric reasons for that, because when you multiply two complex numbers, you multiply their moduli together and add their arguments. So in particular, if you square a complex number, you square its modulus and you double its argument. You square the modulus and double the argument. So if you want to do the square root, you take the square root of the modulus and halve the argument. So that's kind of the intuition for why the square root is defined as it is. Anyways, this is not meant to be a complete overview of absolutely everything that we've done, but hopefully this puts everything that we've done in a little bit of a context and helps us kind of keep everything straightened out just a little bit. I will try and follow the book pretty orderly from here on out. Okay, but that's just a little quick overview of what we've done so far.